We are going to continue this list of fast things and lasers and X-Fells as we shift over to Sally Tracy. All right, yeah, Sally will be speaking on synchrotron and X-Fel, or sorry, and light source diffraction studies of geologic materials under dynamic loading.
Awesome. Okay. Thank you, Suki, for the introduction, and thank you, of course, for the organizers for inviting me to share some of my work this evening. My plan for today was hopefully to give you a flavor for some of the new capabilities for dynamic compression experiments available at US light source facilities, highlighting some of our recent experiments, both from the Advanced Photon Source as well as LCLS, and hopefully giving you sort of an overview of some of the unique capabilities and applications of these methods to scientific questions in earth science. So briefly, why should geoscientists be interested in dynamic compression? It turns out that the extreme pressure temperature states and the fast timescales that we can achieve with these methods make it a really good tool to study a wide range of processes in earth science. And this, of course, includes things, for example, the synthesis of high pressure phases that are found only in the deep interior of the Earth, as well as their characterization, including things like, for example, thermal equation of state, as well as investigations of high pressure phase transitions or melting behavior. And in fact, these tools provide a means to readily achieve, in many cases, significantly higher pressures than is possible using standard static methods, for example, diamond anvil cell experiments. Beyond this, shock studies also provide a unique capability to look at impact phenomena in real time. And so this allows, for example, for the study of things like shock metamorphism in samples from terrestrial impact craters, as well as the potential to study things like giant impact processes and gain insight into, for example, Earth's early planetary accretion and evolution. So briefly, for those of you who may be new to the idea of shock waves, this is essentially just a supersonic mechanical disturbance that produces a step-like increase in pressure density and particle velocity as it goes through a medium. And so when we shock a material, what we're doing is we're effectively instantaneously bringing the sample from an ambient pressure temperature state to a pressure temperature state on a point on a curve known as the Hugonio, where compared to the constant temperature isothermal compression curve that you might probe in a static compression experiment, the Hugonio actually defines both the steeper curve in pressure volume space, but also involves significant heating, as there's no real time for heat flow out of the system during these measurements. And then on release, the material typically follows what is sort of a quasi-isentropic release pathway, such that the pressure quenches rapidly, but the temperature can remain high for some time, which has important implications, for example, for understanding and interpreting both recovery experiments as well as material from natural impact sites. And so what you can see here is that from these experiments, we really have the potential to cover what is a wide range of pressure temperature states. And with these experiments, we can actually readily span the full range of pressures and temperatures that we expect in the Earth's interior, making this a really valuable tool. And so typically when a shock passes through a mineral, the crystal will undergo a series of changes. And so this involves elastic compression, usually at lower stresses, followed by plastic deformation and phase changes at higher stress. And of course, in any shock experiment, the high pressure state is transient. And so you're eventually going to have a release wave that brings the material back down to ambient pressure. And this release often involves further phase transformations or other microstructural alterations that may occur. And so as you might imagine, in order to sort of characterize these processes, the development of in situ X-ray probes is a really valuable tool. And while using traditional methods that have primarily relied on things like velocimetry, allowing us to determine things like pressure, density, equation of state, as well as measurements like sound velocity. The development of new in situ X-ray probes really makes it possible to do things, for example, like identify the crystal structure when materials undergo phase changes under dynamic loading, as well as do things like more advanced characterization of things like transformation mechanisms or potentially deformation behavior that we may be able to assess with in situ diffraction. So typically when we talk about generating shock waves in the laboratory, we can use a range of different drivers. This includes things like a gas gun experiment where we fire a high-speed projectile at velocities up to several kilometers per second, which then impacts our target or our sample, sending a shock wave through the material. And so in these types of experiments, the typical duration of the uniform stress state that we can achieve is on the order of hundreds of nanoseconds up to a microsecond. A second method of generating shock waves in the lab is using a high energy pulse laser, where here we focus the laser onto a low Z ablation layer, which is affixed to the rear of our target. And that generates a plasma which expands backwards, sending a shock wave forward into our sample. And so here for this type of experiment, the duration is typically shorter, on the order of only a few nanoseconds. And then finally, I'll mention briefly that there's also pulse power experiments. For example, the facility that's been developed at the Z machine, which this sort of is provides the ability to generate loading duration somewhere between a gas gun and a typical laser compression experiments. And I believe it was actually mentioned that the other day that this is sort of a potential exploratory idea for a possible e-hutch addition at HPCAT. So I'll just briefly mention in addition that in the last several years, there's actually been a really large increase in the number of user facilities in the US which provide access to do dynamic compression experiments. And so this includes things like dedicated pulse power and high power laser facilities, for example, the Z machine at Sandia, as well as the Laboratory for Laser Energetics, which houses the Omega Laser facility at the University of Rochester. But also we've seen new light source-based facilities, and this includes facilities, for example, the dynamic compression sector, which is a beamline located at the APS, as well as the LCLS and the matter and extreme conditions end station, which has been touched on briefly by other speakers in the session. And these two facilities will really be the focus of the rest of my talk today. So these facilities are really valuable in particular because with this integration of dynamic loading platforms and synchrotron and XFEL sources, it really then opens the door to carry out what is high resolution X-ray diffraction on the nanosecond timescale of these types of shock loading events. And so in the next several minutes, I'm going to highlight two recent studies that we've worked on. The first being a gas gun study that was carried out at the Advanced Photon Source, investigating the shock compression behavior of silica. And then the second, a study that was carried out at the XFEL source at LCLS, looking at the dynamic loading behavior of calcite. So the dynamic compression sector, as I mentioned, is a recent addition or a new beamline at the Advanced Photon Source located at sector 35. And the DCS sort of provides a range of experimental stations that couple different dynamic loading platforms with synchrotron X-ray diagnostics. So today, I'll talk specifically about experiments that were carried out in the gas gun or impact launcher station at DCS. And so here on this slide, I show a few photos that were taken in the hutch in the e-hutch at DCS. And it's a rather large hutch. As you can see, it houses a two-stage gas gun, which is positioned at some angle to the incoming X-ray beam. And these photos on the bottom show examples of a target for these experiments with various optical probes attached. And in this figure on the bottom left, I show a mounted target at the end of the barrel of the gas gun where the X-ray beam would come in here at some angle for experiment in transmission geometry, and the detector sits directly behind that target chamber, which is closed and pumped down in any of our given experiments. I'll briefly mention that in addition to the impact launcher station at DCS, DCS also houses a newly opened laser shock station, which has a 100 joule pulse laser. And so that allows for the routine achievements of pressures in excess of around 250 GPa. And so this is actually a kind of interesting configuration where the incoming drive laser is actually mounted on what is sort of like a rotating arm. And so that can actually accommodate a range of different X-ray angles in the target chamber. So this actually provides some interesting new opportunities to explore, for example, different geometries of off-axis X-ray diffraction, and potentially allow for new opportunities to explore things like strength and texture under dynamic loading. Of course, though, a primary challenge of these experiments is these are all isolating a single X-ray pulse in collecting data. So at DCS, that corresponds to around 10 to the 9th photons. So that we're quite photon starved in these experiments compared to a typical synchrotron experiment where you might average over on the order of 1 billion pulses. And so at the synchrotron, in the experiments at DCS, to mitigate this problem, we use a relatively large bandwidth pink beam. And so here on the right, I show an example of the measured spectral flux for one of our recent experiments at DCS. And so you can see from this measurement that the source itself has a relatively broad bandwidth and an asymmetric peak profile. And so that's actually reflected then in the peak shapes in our data. And so from the silicon calibration on the left, you can see that we see asymmetry and broadening in the peaks. And so in order to accurately then calibrate and analyze our X-ray data, we then have to sort of account for this additional broadening from the source, which at times can be challenging if you're looking at closely spaced diffraction peaks, for example. So the first study that I'm going to talk about is a study that we used the gas gun at DCS to investigate the shock compression behavior of SiO2. And of course, silica is one of the most abundant constituents of the Earth's crust and provides sort of an archetype for silicate minerals of the deep Earth. And then furthermore, the behavior of silica under dynamic loading conditions is really important also for understanding and modeling the effects of meteorite impacts, as well as understanding things like shock metamorphism in samples from natural impact sites. So of course, based on the SiO2 equilibrium phase diagram, which is well established, we know that the 4-coordinated low pressure polymorphs should transform to the 6-coordinated stishovite phase at relatively modest pressure. However, it's unclear if there's kinetic barriers to these types of transformations during these types of ultra-fast loading experiments. And this, whether this transformation occurs has actually been the topic of some debate in the community. And so to address this, we carried out gas gun experiments at DCS. And in these experiments, what we do is we take advantage of the pulse time structure of the beam at APS in order to collect a series of X-ray diffraction frames on loading and release. And so in standard operating mode or 24 bunch mode at APS, you have a train of 100 picosecond pulses, which are then separated in time by 153 nanoseconds. And so then how these experiments work is that the incoming projectile fired by the gas gun interrupts an optical interrupt in front of our target. And this then triggers the gated collection of a series of 4 X-ray diffraction frames where we isolate a pulse with each of those gated images that we collect. And so in this way, we're then able to collect a series of 4 snapshots as the shockwave traverses the sample and during the subsequent release process. And so this shows an example of the geometry that we're using in these experiments, where we're using a transmission type geometry. And in this case, the duration then of a given experiment is actually set by the transit time of the shock wave through our sample. And so in these experiments, we're using silica samples of a few millimeters in thickness, which gives us transit times of 200 to 300 nanoseconds before we see release after the shock reaches the rear surface. And so this is actually kind of important because one caveat of these experiments is that when firing a gun, you can't control the detonation time with respect to the bunch structure of the ring. And so in effect, that means that we can't control the first frame time relative to impact to within 153 nanoseconds. So in that case, we need to ensure that the transit time through our sample is necessarily larger than 153 nanoseconds to ensure that we are able then to capture a frame during the compression phase as the shock initially goes through our sample. And so to get into some data, this shows the results from an experiment where we shocked silica glass to a pressure around 50 GPa. So the stack of X-ray diffraction patterns shown on the left illustrates the 4 frames captured during this experiment. And so the first frame is prior to impact. The second frame the shock has gone around 30% through our sample. And then here in the third frame, the bulk of the sample is in a uniform 47 GPa shock state. And the final frame is collected after the initiation of release. So this 2-dimensional image, which is shown on the right, is corresponding to that third frame. And here we see that the really bright diffraction spots that you see are single crystal diffraction from the lithium fluoride impactor, whereas these powder-like rings are from the SiO2 sample, which has transformed to the high-pressure stishovite phase. And so this sort of confirms that indeed we are transforming to the stishovite phase during these sort of rapid compression experiments, which of course has implications for our understanding and interpretation of, for example, equation of state data derived from shock experiments, but also this opens the door for new research, for example, targeted at exploring physical properties of shock synthesized stishovite under the sort of well-constrained high pressure temperature conditions that we can generate in this type of experiment. So one example of this was a recent study led by Berryman et al., where the authors then used gas gun measurements to look at sound velocities of silica glass in this region where we demonstrated stishovite formation, and then applied these results in order to understand silica-rich regions of the deep earth. So in addition to looking at experiments where we shock synthesize silica glass, we also use DCS to carry out a series of experiments on alpha quartz starting material, which is of course a more geophysically relevant material, at least for understanding things like crustal impact processes. And what we observed here were some interesting differences between what we saw for silica glass, in that we also observed what appeared to be a clear phase transition at high pressure, although a careful analysis of the X-ray diffraction data suggests that it isn't actually consistent with the stishovite phase. And most notably, we can see this in terms of the absence of the strong stishovite 110 peak that we would expect for crystalline stishovite that we see clearly for fused silica, but not in the alpha quartz starting material. And this was actually consistent across multiple orientations, suggesting it isn't some sort of textural effect. And so it appears that while we are observing a high pressure crystalline phase transition on the Hugonio, the phase actually doesn't correspond to well-formed stishovite as has been widely assumed. And instead, our analysis of the data actually suggests that we're forming what appears to be a nickel arsenide type structure, which can actually be described as having a similar HCP oxygen sublattice as the stishovite structure. However, rather than having sort of well-defined silicon atoms filling every other octahedral void in this HCP oxygen lattice along the rutile 110 direction, instead, in this nickel arsenide structure, we have intrinsic disorder where the silicon cations actually randomly fill half of the octahedral voids within that HCP oxygen sublattice. And so what we can take away from this is that the observed structure appears to be having some unique characteristics likely associated with kinetic limitations of the Stishovite transformation, where interestingly, it actually appears that the oxygen sublattice is able to respond rapidly to loading and transform through some sort of displacive mechanism, where the silicon ion motion is likely diffusion limited and therefore shows kinetic limitations. So this is actually a really interesting result in that it sort of challenges the validity of what's sort of been a longstanding interpretation of the quartz eugonio, but also gives us some new ideas about what are sort of new mechanistic details that we can understand about the transition. And in particular, versus what we saw in silica glass, where we had these smooth powder-like rings, the high degree of texture that we see in the high pressure phase indicates that we have sort of a displacive mechanism of the crystal structure to get to that high pressure phase, which does call into question some recent molecular dynamics simulations, which showed that under shock loading, there would be amorphization followed by Stishovite nucleation and grain growth. It's also interesting to note that depending on the initial orientation of the crystal quartz, we observe what are unique transformation textures. So if we load along the alpha quartz X, Y, or Z direction, while the integrated diffraction patterns are all similar, we do observe what appeared to be unique two-dimensional diffraction textures. So moving forward, we're actually really interested in using more sophisticated analysis tools to begin to interpret these transformation textures as well as their time dependence. And while we haven't done this yet for quartz, I'm going to briefly show one example where we sort of begin to develop these methods for simpler archetype oxide systems. And so here we've done an experiment on zinc oxide, which crystallizes in a 4-coordinated Wurtzite structure and undergoes a phase transformation into the 6-coordinated Rothschild phase below 20 GPa, which is actually a phase transformation which is common to a whole host of Wurtzite and zinc blende compounds. And here at the bottom, on the data on the bottom shows the series of 4 frames that we collected during this experiment, where the first frame is collected prior to impact. And so we can use these Lowry spots to understand the initial orientation of our sample. And then here, the second frame corresponds to 80 nanoseconds after impact. So this is here a uniform 20 GPa stress state, and the final 2 frames show the results of some release. And so similar to what we saw in alpha quartz, these data show what are highly textured scattering above the phase transformation, with unique transformation textures that are both reproducible and depend on the loading axis of the initial Wurtzite phase. And so here I show 2 diffraction patterns that were collected for loading along the A-axis and along the C-axis. And here for the C-axis loading, we appear to preserve what looks like large crystallites through the transformation, whereas along the A-axis, we have more extended lines suggesting potentially enhanced plastic deformation along this direction. And so we can then take this data to carry out 2-dimensional refinements and interpret these results in terms of orientation relations between low pressure structures and high pressure structures. And these results are consistent then with what have been the predicted transformation mechanisms for this type of system. And so while of course zinc oxide isn't necessarily an earth critical material, these results sort of demonstrate the types of tools that we can begin to apply to more complex systems, including silicates, to potentially understand phase transformation mechanisms as well as deformation behavior using these types of time resolved dynamic compression experiments. And so in the remaining time that I have left, I'm going to change gears a little bit and talk about a second set of experiments on carbonate samples using laser drive compression at the LCLS using the matter and extreme conditions end station. And so of course, calcite is an abundant carbonate phase in the Earth's crust, and the high pressure temperature stability of carbonates can be important for understanding carbon stability in the deep Earth. And then also being abundant in the Earth's crust, it's important to understand the dynamic loading behavior of carbonate phases, in particular characterize things like solid-solid phase transformations, potential shock melting, as well as the possibility of potential degassing, which would be associated with the dissolution of solid residual phases like calcium oxide, which is something that's been proposed to occur on release in an impact and potentially play a role in the evolution of the atmosphere after these types of large-scale impacts. And so there's been a number of static studies that have investigated the high pressure, temperature, compression behavior of carbonates, which show a series of phase transformations to various low symmetry phases, including things like calcite 3 and calcite 6 and calcite 7, which effectively involve sort of reorientation and tilting of the carbonate groups in the structure. In addition to this, there was actually some early shockwave studies that also identified a phase transformation in calcite around 20 GPa. However, based on the known phases at the time and thermodynamic considerations, they were unable to identify what the high pressure structure was. And then furthermore, there's been shock studies trying to target the identification of potential degassing, which has been a topic of some debate where there's been widely different reported results for the amount of potential degassing that may occur, in particular during the release process. And so we revisited these types of shock measurements and carried out some in situ measurements at the matter and extreme conditions end station at LCLS, where this figure just shows a schematic of the experimental setup, where here are the two arms of the 60 joule drive laser impinge on our target, generating a shock in the sample. And then we can collect pump probe X-ray diffraction in a transmission geometry. We're using a range of detectors. We can then get good angular coverage for our experiment. And so here I show a shot that was collected at 25 GPa for a polycrystalline limestone starting material. And so here we observe from this experiment that we do indeed appear to undergo a phase transformation at this pressure, and a comparison with various phases that have been observed in static compression experiments suggests then that the structure is consistent with this calcite 6 structure. So one interesting thing we can do with this is potentially then use this data in combination with the static compression results to potentially try to get some constraints on thermal equation of state, for example. Another unique thing we can do at the XFEL is do a release time series, where in this case, we're shocking our sample to 40 GPa and then delaying the XFEL.
Sally, you are out of time, so if you could try to wrap it up right here, that would be good.
Will do, okay. And so essentially, in this case, we observed a release time series and saw no evidence for any sort of calcium oxide formation. And then finally, we can observe shock melting at the highest pressures at 60 GPa. And so then briefly, I just wanted to point out that these provide, important new capabilities for understanding phase transformations, kinetics, and metastability for materials under shock loading. And then in terms of, future directions and outlook, there's some really interesting things that we might do with these types of experiments. For example, getting more insight into phase transformations and deformation behavior, as well as look at melting along the Hugonio and potentially look into studies of liquid structures. And then furthermore, in terms of outlook, with APSU, of course, increased flux is a huge benefit to single pulse diffraction experiments, although there's potentially some challenges with new fill patterns. And then furthermore, I think a key thing to look forward, to advance in this field is, of course, sort of doing a better job of overcoming barriers to entry to sort of the larger academic and geoscience community that might be interested in taking advantage of these tools. So I'll leave my acknowledgements and stop there and apologize for potentially going a few minutes over.
Thanks, Sally. I'm going to ask if anybody has any questions for you, that they can please put it in the chat so that we can move on to the very final speaker that we have in the session and the meeting.